Okay. In the last part, we're going to talk about it as another algorithm. It's called CART. The CART is short for classification and regression tree. So this is classification and a regression tree. So CART. Previously, we only talk about any classifications, and we only demonstrate all examples with the classifications. We didn't talk too much about the regressions. But in fact, I mean, we have a talk about this. The decision tree can be used on like regression as well. So this is basically an algorithm and the techniques can either do classification and also regressions. Depends on whether target value is categorical or numerical, like and respectively. There are also a couple like issues in C4.5. Is this whole thing is quite slow if data is large, and this is not a binary tree. So and usually if we are working with a binary tree, there are a lot of good data structures that can make things more like optimized. But like C4.5 and ID3, the decision tree that generated is not binary trees. So that would be like, and a lot of other like redundancies need to be considered. So it would be great if we can just create a binary trees. So CART actually use a different matrix called Gini impurity. It doesn't have the logarithm and the calculations, and it can always generate the binary tree. And since this is regression and the classification, so it can work on the regression and the classifications on both situations. So this has and a lot of field can be applied. So what is the Gini impurity? So Gini impurity is very similar to information gain. It is also a measure on how a randomly chosen element from a set to be incorrectly labeled if it was randomly labeled according to the distributions of the label in subset. So I mean, this is kind of like quite complicated. So this is, and what does that mean? Said the formula is given as follows: is if you have a set of S with k different target classes, the Gini impurity is being given as follows. It's basically sum of I to the k of pi times 1 minus pi. And this can be further simplified by taking advantage of summation of pi of I is equal to 1. Then if we factor this out, that becomes 1 minus the summation of I of pi squared. Okay, so like how does that, I mean, so actually to be interpreted, so that means if you have just a zero and a plus and minus and for say, then I mean, if it is like randomly labeled according to the distribution, which and in the cases that will be just p and was 1 minus p. So how, I mean, this is just for a very simple and a situation to be considered. How often a randomly chosen element from the set to be incorrectly labeled. So that means I'm going to choose and label and one that is just like so randomly chosen. So the probability to choose like, and this is say plus, this is minus, to be plus is probability of p. Then I'm going to randomly label, I mean this this data with this corresponding distributions, the probability that being labeled incorrectly is that would be P times the 1 minus P, because I just labeled it with minus instead of plus, right? And this is, situation if I pick the plus. But if I pick the probability that pick the minus, that will be 1 minus P. And then the probability to labeled incorrectly, that will be P. So this will be the total probability, or total probability that is randomly chosen element, but would be incorrectly labeled, right? So that, that would be the situation of the probability that we have. Is that clear? Or we can do a little bit like more complicated. For example, we have probability of P1, P2, P3. Say we have a 3 object, right? So, and that corresponding to A, B, and C, we know P1 plus P2 plus P3 equal to 1. Okay. So if you randomly chose an object, so there will be probability of P1 that you picked A. Then you label them according to, these distributions. It will be 1 minus P1 that you are labeled incorrectly. Right, so this is, probability that you pick for A, but just and the label incorrectly for A. Then you continue this for B, then and the probability to pick B is P2, then you label incorrectly. That will be 1 and 1 minus P2, and you do the same thing for C. So this is called Gini impurities. All right. So, and also this is quite interesting. If a node is pure, that means my Gini impurity is equal to 0. That means all the examples belong to the same target class. So that means if I'm working and Gini impurity is equal to 0, if and only if 1 of Pi is equal to 1 for some I. Right, so this is, quite obvious if you just look at this whole thing right here, and this, expression equal to 0, that implies the Pi square, sum of Pi square, that should be, equal to 1, but that only happens if 1 of Pi equal to 1. Okay, so if you have, so a node with many examples from different target classes, then you will have the Gini impurity is close to 1. So that means if Gini impurity is kind of maximized when Pi is, is uniform. So this is basically very similar to what we already talked about in entropy part. So that means if it is uniform distributions, then it's like each element has equal probabilities. Then the Gini so Gini impurity is and it's maximized here. So in some senses you can think about this Gini impurity is kind of tail expansion of the entropy here. So you have this log of 2x, which is log of x divided by log of 2. If you actually do this tail expansion, this becomes -1 plus x, right? So if you have this, trying to do this and a tail expansion, then you nothing, just plugging this into the summations, then you will find out this Gini impurity is kind of approximate to this entropies with some constant ratios. Right, so this is quite interesting, but of course this is just purely an approximations. But why this is and Gini impurity is better than like entropies. The reason is pretty straightforward. It's because the entropies actually we need to take the logarithm. In computation, I mean, so in computer, if you take a bunch of logarithm again, it would take, I mean, the whole process will be quite expensive. But in terms of Gini impurity, we only doing some square of the probability and then sum them together. This is significantly cheaper than take the logarithm. So that's why in scikit-learn, it's much more preferred to using Gini impurities rather than the entropies. All right. So then how do we do this and find the features? And also in these cases, if we are doing continuous features and we are not going to find the root like automatically, in fact, we are trying to think about the way that we are trying to do the and splitting, because we are thinking about the way of a continuous values in R that we are splitting some threshold right here, that and like everything to the left will be in the left branch, everything to the right will goes to right branch, right? So so this is very common way and to think about if the feature is a continuous variables. So and what is the optimal and splitting going on here? So this is very similar to the idea of and to maximize the information gain or information gain ratios is I want this node to split that the Gini impurity of the children, which is and the left to the right, is I will call it average Gini, and average Ginis of the children weighted by the size is minimized. So basically, I want to split on this threshold such that Gini impurity of the children is kind of minimized. And in some senses, you can think about it roughly as the information gain is maximized, right? So if the Gini impurity of children is minimized, that means the Gini impurity gain is maximized. So I mean, and I hope you can understand the like and the like minimization part versus maximization part. So mathematically speaking, if we have a set of S split into S1 and S2, that means we have some like threshold that is X is in the A and X is not in A and belong to S1 and S2. So the key is we want to find the threshold that this Gini impurity of the children, which is defined as Gini impurity of S1 and Gini impurity of S2 weighted by the cardinality of S1 divided by cardinality of S versus cardinality of S2 divided by cardinality of S. So, and this is basically the an average Gini impurity of the children and weighted by the size. So this whole thing, I want this whole thing to be minimized. So I want to find out such like optimal feature and the threshold such that this thing is being minimized. So that means we need to find two things. One is optimal features. Another thing is and a corresponding threshold. So we need to search through this. Okay, so how we're going to like work through this? And of course, that's not easy at all because we are having the continuous and features, and this threshold can be set anywhere, right? And it's not necessary to be set at one specific point like what we did for discrete values. But for the continuous features, it can be set anywhere, like in R. So that means that will be very hard to find the threshold in general. So we need to think different ways. So what you do is you are going to iterate through all sorted like feature values as possible threshold. So you think about, I mean, since everything is on the real, so we can sort them out. So that means we have, say, X1, we have X2, we have X3, we have X4, we have X5. So we don't need to worry about the threshold. We only need to worry about where we want to split those data. So do we want to split here that we have X1, X2 being one branch and X3, X4, X5 into another branch? Or do we want to split right here that X1, X2, X3 in one branch and X4, X5 into another branches? So that means we have all these candidacies of the threshold and which is just being the midpoint of two nearby and the two nearby feature data. So these are all possible and the threshold. So these are all possible thresholds. So only thing that matters is like you need to keep track the number of like examples on the left and branch or and on the right branches. So you are going to increment or like decrement by one as if we move like one threshold. So and we can and then easily compute this Gini impurities in constant time. So instead of you work on the threshold, you work on the like datas on left branches and the right branches. So for example, right here, say we have the data that we have and the split is it's 1.5, 1.7, 2.3, 2.7, 2.9. So and let's just say this is 1.5, this is 1.7. Of course, that's not really scaled. 2.3, 2.7, 2.9. Okay. So and what you're gonna do is the whole idea is you are going to start with everything say in one basket. So you're going to think about say if I mean this is my left and this is my right. So you first with everything say on the left and the right will be empty. So you calculate the Gini impurities, right? So then you're going to move one point and from left to right. So you're going to have X1, X4, then X5. So basically, instead of you change the threshold, you just move the point, right? From the left branch to the right branch. So you calculate this Gini impurities of SNA, and this is another and SFA2 and so on. And at last it will be X1 to X2 to the X5 and empty to X1 to X5. So you calculate all possible Gini impurities for all 6 of that. So that's equivalently that you move this threshold along the real lines, right? So this is and how we do it. I mean, this whole code right here, just calculate the Gini impurity. It's like fairly straightforward. All you need to do is just to find the like corresponding ratios right here, which is n and divide by m. So this is basically the p of I. And you have p of I and a square and sum them together. And one subtract to that. And that will be your like any Gini impurities in general. So in this cases, I mean, for this specific data right here, the Gini impurity right here is just 0.64 right here. So what I hear is, and this is the and a function right here to do this kind of best split based on what I just mentioned here. So the best means the average impurities of 2 children populations is smallest possible. Okay, and also and it must be like less than the purity and impurity of the current one. So the way we do it is we loop through all possible features and consider all the middle point between these like training samples as possible threshold. So that means we like start everything from left and being empty on the right, then move one by one. And this is equivalent to consider all possible like and a threshold. Then we compute all the Gini impurities for all these split, and then we're going to return the pair, which has the smallest impurities possible. So and let me just demonstrate with the code right here. Okay, so you can see we have the split right here. So this is the main code right here. I think I was like slightly different. So like initially I will start with my left and the left branches to be completely empty, and my right branches to be full and has the whole data here. Then what we do is we move the point one by one, and for each point we are going to for each split, and we are going to calculate this Gini impurities. And this and the Gini impurity for the and this is the Gini impurity of the left, and this is the Gini impurity of the right. Then we're going to weight them with the weight them with and with the size, right? So and we have I divided by n, and then we have m minus I divided by n here. If we find out this Gini impurity is less than the current best and Gini impurities, then I'm going to replace this best Gini into Gini, best feature into features, and best threshold, which is basically the threshold of that corresponding I and I minus one. So basically the midpoint of these two and the 2 points to do the split. That would be the threshold that actually matters. All right, so this is basically we need to loop through all the data, and also we need to loop through all the features, right? So for all the features, we need to loop through all possible split point. Then we basically search all possible like possible way to split the data, and to find out the best features and the best threshold to minimize the Gini impurities. Okay, so it's basically like the most and the like dumbest ways just to do the search, right? So we like and loop through of everything, just find out the minimum of that. Okay, so if we do that, we find out for this specific cases the best feature, which is x, of course, because we only have one feature here. But the most interesting, the most interesting part here is we are going to separate this at 2. So that means 1.5, 1.7, they are classified at 1, and 2.3, 2.7, 2.9, they are classified at 2 and 3. So if we set a threshold at x equal to 2, that means it can separate y equal to 1 versus 2 and 3, right? So this is the first step to separate this x out and to separate the y out. So this will be the first threshold that you should set up here. And of course, it makes perfect sense, I would say. All right, so and we can make some and work on some testing data sets. So this is iris data set. We have sepal length, we have sepal width, petal length, and petal width. So these are the 4 features. And we have a target. Target is like 0, 1, 2, 3. It's different type of iris to work with. And everything else is being very similar. That's what we got here. But the difference is we need to instead of using the information gain here, we are using this best split with a cart and by using the Gini impurity and to minimize the any Gini impurity as our like objective. So if you do this, then we are going to go through this whole code and one more time. But the difference is here, and we need to like specific tells and what is and the like left variable and what is right variable. And previously it's just yes or no, but in the continuous settings it will be less than some threshold or bigger than some threshold. So just and this part will be and that node part will be slightly different. All right, so this is basically what is being done. Everything is basically same. We still build up trees recursively, and if we got like and the set is being pure, that means there's only one value that we will and assign this one to, I mean, as the leaf of the didn't trees, and otherwise I will keep looking through and getting this and calling this and build trees again and like recursively. But the differences in this situation is in cart, if we are working with a continuous feature, you can reuse these features right here. So once you use these features, for example, this X right here, you can reuse it again, right? Because if you look this and the data set right here, you can like easily think like, and everything less than 2, that will be classified as 1. Everything like less than 2.8 and bigger than 2, that will be classified as 2. And everything bigger than 2.8, that will be classified as 3, right? So this is basically you would do if you want to make like separations. So that means, so let me just using the like notepad one more time. So these are basically ones, and twos, threes. So basically what you should be working with, and we know, so with a card we know this, and at first we set the threshold right here at equal to 2. If you keep like building this up, then you're going to set on the second one, you're going to set the threshold right here equal to 2.8. So that means if it is bigger than 2 and less than 2.8, that will becomes 2. And if it is bigger than 2.8, that will be 3. So basically, if you want to build a tree based on this simple data, so the first node that you're going to do is the threshold, whether X is bigger than 2 or not. So this will be your node. If yes, then a no. And if no, then it will be always 1. Then you are going to set a threshold that is X is whether it's bigger than 2.8. If yes, this will be 3. If no, this will be 2. So this is and what is card will give it to you. All right. So let's see whether it's giving you this result. Let's work out. Okay, so decision tree of DF. Okay, so DF. This is best feature DF. Okay, DF. Let's rerun these things. And Okay, just a second. Okay, so I need to make some changes here. So there's I need to make sure this df node right here is actually float, so we can compare with the values with the best thrashed right here. I mean, if it is like an objective, and which is string, and that I can and not compare the values. So that's why if we change this, actually we can just directly apply, I mean, this function right here. Then this is my tree is being built up, and this is exactly what and what I just mentioned. If it is like less than 2, this will be 1. If it's bigger than 2, then check whether it's less than 2.8 or is bigger than 2.8, and that corresponding to the class of 2 and or class of 3. So if we work with the data for the iris, and this is the and basically the same thing, and then you will see this is the tree that being built up. This is, I mean, it's quite complicated. You have like 1, 2, 3, 4, 4 different layers. The first thing that you check is whether this petal length is less than 2.45. Then you check whether the as a petal width. Then you check petal length again. Then you check the petal width and it's like sepal length. And you will find out this sepal width is never being used in this situation. So it is totally possible you build up the antecedent tree using COT algorithm and without using one specific features, right? As you can see right here, we're only using 3 features that perfectly to separate all these and the situations. Okay, so that's basically I want to talk about here. I'm going to update this notebook after that. And of course, that's not the end of everything. We haven't talked there's anything on the cross validations. We haven't talked anything on the pruning. But like for the cross validation part, and we're going to talk about in detail in practical machine learning part. But for this whole courses, we're only going to focus on the theory of the decision trees and how we train and fit in the decision trees using 3 different algorithms. One is ID3, one is C4.5, another one is CART, which is given right here. Okay, so that's all for now.